everyone, this is Miss Weidenhammer, and today we're going to be talking about biotechnology. Specifically, we're going to be talking about three realms within biotechnology: gel electrophoresis, genetic engineering, and cloning. So today, for our classwork, we're going to be taking notes on a piece of paper or the attached notes that can be found on Google Classroom. And for homework tonight, you are going to answer the practice questions that are based off of the notes that we take today on biotechnology. So today we're first going to start off with gel electrophoresis. You might have heard the term gel electrophoresis before. Let's first take a look at a definition of what exactly gel electrophoresis is. So gel electrophoresis is a laboratory technique that's used to separate fragments of DNA in an effort to identify its origin. Now, gel electrophoresis has a list of procedures that you need to follow. But before we get into that, I want to first take a look at the different materials that are used so we know what we're talking about when we're talking about the procedure. So first we have the chamber, and the chamber is going to hold the gel and the buffer solution. So looking at your image, this gray outline here is going to be acting as our chamber. And inside we're going to have the gel, which is this big rectangle, and our solution, which is the liquid that the gel is in, is going to be the green that's throughout. There are also electrodes attached to a power source and the chamber to allow electric current to run through the buffer. So in the image that we have here, we don't see the electrodes, but they would be at the two ends of the chamber. So they would be here on the negative end. They would also be attached here to the positive end. The gel contains pores to hold the DNA and allows it to move towards the positive end. So again, taking a look at our image, it would be this rectangle that has these little rectangles or pores, okay, and goes from the negative end down to the positive end. Okay, the wells at the negative end of the chamber hold the DNA. So these tiny rectangles are going to be holding our DNA, and the buffer solution is the solution that carries the electric current through the chamber. So it's going to be the liquid solution that the gel is in. And again, the current is going to go from the negative down to the positive side. So let's take a look at the procedure step by step of how you go about doing gel electrophoresis. First, restriction enzymes are going to cleave DNA into smaller segments of various sizes. So it's going to cut the DNA into different fragments, and that's going to be done in a separate test tube. It's not going to be done in the chamber that we discussed earlier. So once our DNA is cut into segments by this enzyme, we're going to go over to step 2. So now the DNA segments are going to be loaded into the wells in the gel. And again, the wells are right here, these tiny rectangles. And again, remember that the gel floats in the buffer solution within the chamber. So we're going to insert the DNA fragments into each of these wells of the gel. Third, when an electric current is passed through the chamber, DNA fragments move toward the positively charged side, or the positively charged cathode. So we have now placed DNA in these wells. When the electric current goes through, it's going to go from the negative side and flow through to the positive side. When this electric current flows through, the smaller DNA segments or fragments are going to move faster and farther than larger DNA segments. And because of this, the DNA fragments are going to make a pattern on the gel. So the DNA fragments that are smaller are going to move farther down the gel, whereas the DNA fragments that are larger are going to stay closer to the wells that they were originally in. So let's take a look, let's do a little review of what we just talked about. So what we saw in that image was a DNA fingerprint. It was the pattern that the DNA fragments made. So how exactly did we get that? Let's do an overview of the procedure that we just talked about. So first we had to collect DNA samples. We then cut those DNA samples using a restriction enzyme and made fragments out of them. Before we can load them into the gels, we need to add a stain or dye to them so we can see how they're moving throughout the gel. We're then going to load the gel with those DNA fragments. Okay. And when we allow the electric current to run through, the DNA is going to be separated by size. So remember, the smaller pieces are going to move faster and farther. The DNA is negative, and therefore that's why it moves from the negative to the positive end of the gem. And once that is complete, you can read the results. You can see how those fragments of DNA were separated based on their size. So why would we use gel electrophoresis? Let's go through some reasons why you would use it. One scenario is using it in a crime scene. So let's take a look at the picture that we have on the screen. Let's say scientists or analysts were at a crime scene and they were able to get a blood stain, some evidence from the crime scene. So they were able to get blood, and from that blood get DNA. They went through the procedure of being able to put the blood's DNA through gel electrophoresis. Let's say these crime experts knew who the suspects were. Say they had Bob, Sue, John, and Lisa. These scientists are able to get the DNA from Bob, Sue, John, and Lisa and compare them to the DNA that was found at the crime scene. So using this, they can see who exactly could have been at this crime scene. So let's take a look at how you would do that. If you take a look at these different fragments of DNA and how they got separated from the blood stain, you can compare them to each of the suspects. Let's first take a look at Bob and see if his pattern matches up with the blood stain. The first one does match up. Second one matches up, but he's missing this third band. So we know that Bob is out of the picture. He was definitely not at the crime scene. Now let's take a look at Sue. Let's see if Sue was there. Sue matches up with the first band. Second band matches up. Let's take a look at this one. Okay, so this blood stain, the one that was found at the crime scene, does not have this band that Sue has. So we know that Bob and Sue can be taken off the list of suspects. Now let's take a look at John. John again has that first band matching with that original blood stain. Second one, yep. Third one, yep. Fourth one, yep. Here we have one matching up as well. Oops. Taking a look at this also matches up with the blood stain. Taking a look at these two, those match up, and this band matches up. So we know, without even looking at Lisa, that John matches up perfectly with the blood and DNA that was found at the crime scene. So using this, forensic analysts, forensic scientists would be able to know that John was at the scene of the crime. Who knows if he was a criminal or the suspect? That would have to be based on the different things that they see at the crime scene. But we know that John was present because his DNA fragments match up with the DNA that was found at the crime scene. Another reason for gel electrophoresis is to do a parent analysis. So let's say you had a child, you could match up the child's DNA fragments with the fragments of the mother and the father based off of gel electrophoresis. So let's say you knew who the child's mother was, but you didn't know who the father of the child was. You could look at the child's fragments, DNA sequence or DNA pattern from the gel electrophoresis and try to match it up. So looking at this child, this first band came from the mom. This second band is not present in the mother's DNA, but is present in the father's. Okay. Moving down, this band is present in the mother, but not present in the father. The second band came from the father then. And this third band, both parents have it, so it could have come from either. So let's say you were taking a look at a picture like this. Let's say you knew who the child's mother was, but you did not know who the child's father was. Let's see if you can figure out who the child's father was. Let's take a look at the first banding pattern of the child. Here we go. So we have this pattern. So the mother, this first band, does not have the band that the child has. So let's take a look. Who has this band? Dad 1, Dad 2, or Dad 3? Okay, so Dad 1 doesn't have it, so we know that Dad 1 is out of the picture. He's not the father of the child. Let's look at Dad 2. Oh, he has it, and Dad 3 has it. So right now, we know that either Dad 2 or Dad 3 is the father of the child. Our next band correlates with the mother's band, so we're good with that one. Let's move down to the third band. Our third band matches the mother's once again. Moving down to these two bands, the mother doesn't have these two bands in her DNA fragments, so we have to look to Dad2 and Dad3. Let's take a look at this top one, okay? Coming along here, we can see that Dad2 does not have that pattern or that band, and Dad3 does. So we now know that Dad1 and Dad2 are not the father of the child, but Dad3 is, because his banding pattern correlates with the child's banding pattern in comparison to the mother as well. Okay. And lastly, we can use gel electrophoresis in looking at common ancestry. So scientists believe that species 1 here that has this common ancestry in the image, that's the common ancestor for the rest of these deer species. So the 4 species have some traits in common. They also have traits that are unique to their species. Scientists use the process of gel electrophoresis to study this relatedness of the 4 deer species. So they were able to use the banding patterns of the common ancestor species and deer species 2, 3, and 4 to see if there are some commonalities between the species. And there we have it for gel electrophoresis.